Okay, so this is my workbench up here, and what I've got going on here, this is the work in progress. A lot of times I make my videos, I move these down to the dining room table and I show the video and it's all finished, but I just want to give an update of where I'm at with the EasySpin 3D printed motors. This is version 1, it's the 6-coiler, you know, all the magnets facing out the same direction, all the coils the same direction. This is the 12-coiler with 6 magnets on the rotor, and this is version 3. Version 3 is a version that will let us experiment in every possible configuration. On the back of the coils, I come out with 2 copper posts, and there's a placement to mount this post right on the coils themselves. You can see that. And the coils pop in and out real easy, so we can take them out, wind different types of coils, experiment with whatever we want in that respect. The top part slides off, so rotors can come in and out very easily. The rotors on version 3 are just one single print. On the previous rotors, on version 2, I had 2 halves, they're like a clamshell and they snap together. I discovered these are balanced just fine. This rotor has 1/2 inch by 1/2 inch cylinder magnets in it. You can see that in the light there. You can actually see the 3D print. Inside there's a filler and it's kind of a matrix, and you can see that in there. But anyway, version 3 is going to allow us to experiment with all the variables. And that's going to be really fun. One other thing to point out, right now this one's running along here on this electrolytic capacitor. And you can see the electrolytic, I got the lines. It's connected just like it would be with a reed switch, but instead of a reed switch I'm using a Magnasphere. Magnasphere is something I discovered trying to find an alternative to the reed switch. And I'm in no way saying it's better than a reed switch at this point, but I'm testing it, I'm experimenting with it, and what's interesting about it, I think there's a ball inside here that's making contact with some gold plates as the magnets pull the ball over. But it's just something interesting, you know, another thing that we can use in our research. So yeah, I'll go ahead and put a link to that on Laser Hacker Forum under the prototype build section on the EasySpin 3D printed motors, and I'll include that link here in the YouTube video. But some of the interesting things on version 3, I'll go ahead and just take this little motor apart and show you some of the interesting things on version 3. One more thing on the Magnasphere, these come in normally open or normally closed, so you've got some pretty interesting options with the Magnasphere. But anyway, let's take this apart and I'll show you what I'm excited about with version 3. So version 3, the top pops off here, and this adjusts, the pin adjusts, so you can put different needle lengths on this. Of course, we got our rotor. This rotor has a lot of different options. You can go 3, 4, 6, you know, you can do a bunch of different stuff. Again, you can see the matrix inside there. And then the next interesting thing on version 3 is that the coils snap in and out. There's little, you probably can't see it on that one, but let me take out a few of the others. There we go. You can see the little grooves. These little grooves hold these coils. And if I show you here in the back, you can see the posts for the, I believe it's 14 gauge copper wire that slides into there and lets you solder the ends on. But I'm pretty excited about version 3 because version 3 is going to allow me to test a lot of ideas very quickly. You know, you can set some of these up as driver coils, some as generator coils. You can experiment with different windings and just snap these in and out. And you can see because of the shape, they're cone shaped. If you want, you don't have to do them cone shaped. I'm also setting up a print that allows more of a pancake coil, so I just put another flat disc just right back here and we can experiment with some pancake coils. But anyway, version 3, very excited about that. I've got my power supply, it's set to 6.3 volts, which is the voltage on this little electric capacitor. This is a 1000 microfarad electrolytic capacitor on the EasySpin version 1. And I've been doing a lot of testing. I mentioned on the forum that I was not getting as good a charge with without the alternating coils. I played with the position on the reed switch and I was able to get a pretty good charge even on the 6-coiler. This little guy will run down into very, very low voltage, like 1/2 volt, pulling like 1 microamp at a pretty decent RPM. So for crystal cells, for experimenting with all this stuff that has to do with crystal cells or low voltage galvanic cells or anything along that line, this little 6-coiler probably is the best that I've come up with for that. So I'm still going to recommend version 1 for crystal cell experiments because you get a great RPM at a low voltage. Right now we're at 6 volts and the RPM would be off the charts if it was not for this diode. I've got a small diode connected down into the coils in series, just like I have in version 2. and that drops the milliamp draw at this voltage, and it will allow us to get a really long runtime on this little electrolytic capacitor. Then over here I've got version 2, and it's just idling along because this is more of a high voltage motor, I've decided, with the 12 coils. A lot of torque, very high voltage, very low current draw. And I'll illustrate all of that here in a second, but both of these together running along are pulling between 4 to 5 microamps. And just think that's kind of interesting. But what I'm going to do now is I'm going to get this guy out of the system, or just basically just disconnect these. And this electrolytic 1000 microfarad should have 6.3 volts in it now, and we'll just we'll set it over here running, and I'll check the voltage on it later in the video. But let me go ahead and connect up this one. And you can see it starting up to run, and you can see its microamp draw as it's accelerating. So as it's accelerating up to speed, it's drawing between 1 to 2 microamps. Let me just set this meter here and show you quickly how this works as a generator. So let me get it in focus. So if I rotate this motor, you can see the needle go negative. That's just from me lightly spinning it like you saw there. If this was not connected up to the power supply at 6.3 volts, this, if it was not connected, this cap would be charging really fast, even with that little bit of spin. At some point here, it will stabilize right around 0. Tell you what, let me put this up to 10 volts because this polyester cap will allow me to go up in voltage up to 100 volts without any trouble. So we'll get this at 10 volts. So we're running at 10 volts. It's going to bounce along here at around 1 microamp. And then it's actually going to drop down below 1 microamp significantly. I do have the ability to take RPM readings on these now. You can see we're at 148. It's upside down, so I apologize. About 144. 44 to 40, yeah, I'd just say 144 RPM, drawing about 1 microamp at this point, and this will stabilize. I've seen this stabilize and draw well below under 1 microamp as the whole thing stabilizes out at around 10 volts. Let me go ahead and increase the voltage. I'm going to just spin the voltage up and let you watch the rotor here as we bring the voltage up. So I brought the voltage up to 73.4 volts, and the rotor's taking off. And now I'm just going to do some experiments with showing you the actual pull on the capacitor in current. You can see here that as the motor is accelerating, the microamp pull is dropping, and it's pretty significant. So it's going to drop down here, down more and more as the RPM increases on the rotor. If I take and give this rotor a blow at any time, let me see if I can get this all in the picture. So I'm going to give it a blow, and you watch the microamp draw. You can see that with that one gust of air, it brought it down to under 20 microamps. So let's just let it sit there for a second, and I will take another RPM reading. So at that, we're at 740 RPM or so, and a little bit of drop on the RPM there as it recovers from me blowing it. So let me go ahead and slow down the rotor. Get it down in a range so you can see what's going on here. So now it's holding, it's actually dropping in current, so the motor should be accelerating. Let's see here, we're at 636, 39, 640. So yeah, the motor's accelerating, 640 RPM or so. And the current draw is dropping. So to give you an idea, at 70 volts, when this thing completely stabilizes, it pulls around 15 microamps if you let this sit for a while and stabilize out. So anyway, that's pretty good. Let me go ahead and disconnect it at this point from the power supply. So now it's just running on the polyester film cap. And What's Up on overunity.com, he's also on laserhackerforum.com, was wondering about me snipping the wires right here. And I'm going to have to come in and try to focus all this out. Let me see how close I can get with this camera. So what I've done is, you can see the reed switch. Let me see if I can get something to point with. This is going to be a little bit technical, but the reed switch is nestled back here, and it comes out, and one wire from the reed is coming along this way over to the coils, which are all connected in series. So from this coil on, the connections are in series. You can see the very fine magnet wire coming along. I apologize for all the solder on these. I've clipped these coils, I've taken them apart, I've connected them in series and parallel as generators, as motors, as drivers, but just so you can follow them along here. They all come around in series all the way back around to this point, and at this point where the break is where I come along and I've got my diode, and the diode is going in this direction. It's a germanium diode. It's coming down this direction to this point and connected in here. You've got the polyester film cap. The other end of the polyester film cap is coming down and running over here to the reed switch. So I apologize if this isn't interesting, but it was requested. And it probably will give a much better explanation as to how this is all hooked up. So anyway, that's how this is hooked up. So this has been running along here. I'm going to go ahead and stop it and see if it has any juice from that 70 volt charge to start itself again, which you can see that it does. So let's go ahead and show you some experiments with how this runs as a generator. And then what we'll do at some point here, we started this little guy out at 6.3 volts at the beginning of this video. At the end of this video, we'll check this guy and do some experiments with him as well. But just wanted to point out that he's still going back there. So anyway, this one's accelerating. I'm going to go ahead and hook up my multimeter here, and we can read some voltages on this cap. Okay, so what I've got is the multimeter set here. I've got the positive line from the capacitor connected to it already, and then I'm going to go ahead and connect the negative, and what you'll see is the actual voltage on the cap, which is 18.64. It's dropping really fast. It's actually dropping faster than reality because this multimeter is showing up as a load. I apologize for the rain outside. It's kind of noisy, but I'll speak louder. So we saw that it was at 17 volts. If I tap here quickly, we can see that it's back at 16.43, so you can kind of get an idea of the voltage drop. But what I really want to show you in this video, let me slow down the rotor. So keep an eye on the voltage here, and I'll add some drag on the rotor, and we'll bring the voltage down on the polyester cap. You know what, it's taking too long. Let me just get some clip leads here, and we'll actually just completely discharge the cap because it's going to take too long to run the voltage down that way. So now what we've got, let me stop the rotor, and we'll drain this capacitor out. Alright, so you can see that the cap here is now at 0. And what I'm going to do now is I'm going to just spin the rotor with my hand and watch the voltage on the capacitor. You'll see that it already went up to 8 volts, 9 volts. Usually with just a simple flick like that, it'll go up to 10 volts or so. Now I'm going to go ahead and blow on this rotor and bring it up to speed here a little bit. So you can see one blow brought us up to about 25 volts. 50, 70, so 4 blows brought us up to over 100 volts on the polyester film cap. I'm going to go ahead and disconnect this now because that provides quite a draw on this little capacitor. I'm going to let this run for a little bit. So what's interesting about that is you see that this actually charges really, really fast and makes a really good generator. And that's one of the neat features on this little motor. So now what I'm going to do is I'm going to apply some drag. Oh, before I do that, let me just show you this. This is kind of interesting. I can connect an LED across these coils. Let me see if I got the polarity right. Apparently not. There. And we've got, let me see if I can hook this in here somehow. So you can see that we got the LED lit just across the coil there, so that's pretty interesting. I'm going to go ahead and slow down the rotor some more. The LED provides drag on the motor itself, but you can see that slowing the motor down and releasing the motor, it speeds right back up. So a lot of work from a polyester film cap. Somebody was wondering how long it would go from a dead stop. So what I'm going to do is I'm going to blow this up to speed. I'm then going to stop it, and we're going to let this rotor start, and we're going to let it run while we test the voltage on this one over here. So let me go ahead and blow this one up to some speed here. Alright, that should be fully charged. We'll go ahead and we'll stop it completely, and we'll let it start. So this one's on its way, and we'll let it run there in the background, and we're going to go ahead and just take a voltage reading on this one, which has been running the whole time, and we'll see what it shows. Let me put that there so you can see the voltage. And what we've got on the voltage on this one is basically 4 volts, 3.98. I'm going to hold it on there and we can see how fast the voltage is dropping. 3.97. So you can see this is a very slow voltage drop, and actually with the multimeter connected like this, I'm dropping the cap much faster than it would normally be dropping. 3.95 to 3.96, 3.95. So that's the voltage drop on this little guy, and I think version 1 is doing really well here, considering that we've got this little tiny, electrolytic capacitor on here, and the voltage drop has been that slow. I'll go ahead and show you a few current readings at different voltages on this one, as well as this one. But let's go ahead and start with this one so we can leave that one running. And this is the one that started from the dead stop earlier. We'll just leave that one alone, and we'll do some experiments with this one. So we'll connect the positive leg up to this through my current reader. So we can read microamps here. Alright, so let's bring this down. And we're going to bring this cap down in voltage. I'm going to short the cap out here. I'm going to bring the cap down in voltage to 1 volt. So I've got my power supply set at 1 volt right now. Let me just stabilize the cap at 1 volt. Alright, so we've got the voltage, we got the power supply set at 1 volt, the motor's running along here in 1 volt, and what we got going on, this is actually showing up in negative territory just because the capacitor was charged at 3 volts previously, and now that we brought it down to 1, it's wanting to bounce back up. That's the reason I went to the polyester film over here. I've got more of these polyester film capacitors, and it's really fun to experiment with the polyester film capacitors because they don't show this bounce back effect, and you can get much more accurate readings with them. So I highly recommend that experimenting be done with the polyester film caps, and I think there'll be a lot of advantages to that. But I will go ahead. Alright, I just had to spend a couple minutes looking for this, but what I've got here is I'm actually building a cluster of these polyester film caps. Each one's 10 microfarads. And I found them. I had a cluster started with 4, and I put that in line to this polyester film cap in parallel. And it really lets me experiment so much better than these dielectric or electrolytic capacitors of dielectric absorption and other issues. But anyway, I will go ahead and solder these together and show you what I mean about that in a second. But going on with this video with this little guy, the electrolyte capacitor has stabilized now. So this is its actual pole. And let me just slow down the rotor here a little bit and let it start. And you can see that this little setup, this little 6-coiler, is going to be excellent on a crystal cell because we're at 1 volt. We're coming from the power supply into the cap and my little microamp meter in line. And I've seen this thing running on 0.5 microamp to 1 microamp consistently. So I just think that's really, really good. I think that's an incredible setup for experimenting and for basically having a visual demonstration of the power that from the little crystal cells that goes on and on year after year. I mean, this one's working much, much better than the one in my live video feed. If you go to laserhacker.com, you can see a live video feed with a motor that's been running for over 1.5 years on a crystal cell. That particular motor, if I remember right, pulls 10 to 50 times what this one pulls. So it would be interesting to hook up one of these to that crystal cell, and it would increase its lifespan dramatically, I would assume. But anyway, just wanted to show the incredibly low microamp draw on the cap. I'm going to go ahead and bring the cap up now in voltage to the voltage that sits on a crystal cell, which is about, whoops, I went too far there, which is about 1.7 volts. So 1.7 volts, which is the galvanic voltage between magnesium and carbon. We'll go ahead and let this stabilize down, and we'll check out the way this thing runs at that voltage. So you can see that the milliamp draw is dropping down here on this, and the RPM will be increasing. I moved it around, and anytime you move one of these, especially at these low voltages, it really messes them up. But it's starting to recover. It will accelerate up here in a second. So just so you can see the generator effect on the small 6-coiler, we're right at 2 microamps on draw right now. I'm going to go ahead and give this a blow and watch the current over there. There. That's the generation effect. So when I gave it the second blow, you saw the needle just dip right down below 0. So the energy that it put into this cap is still going back into the power supply, but you can see now it's starting to stabilize. So now we're actually going to stabilize out, and we will actually see, oh, and by the way, this one is just now stopping. I just noticed that. So that gives you an idea. From a dead stop, I did actually stop and hunt this down for a minute or so, which kind of messed that up, but that gives you an idea. This one runs a really long time even from a dead stop, even on a polyester film cap. But to end the video, I'll do some experimenting with this setup connected together in parallel with this, and give you an idea as to what, let's see here, there's 50, 60, 70, 80, 90, I probably have a 10th one somewhere, I don't know if I'll find it, but give you an idea as to what 90 microfarads on a polyester film cap will do on this little motor. It's pretty cool. But back to this guy, you can see we slowed him down, we sped him up, we did a few things, but now it's stabilizing. And it really is about 0.5 microamp at 1.7 volts. So a great little motor for working with crystal cells. Just exceptional. So anyway, that's the update on that one. Let me jump out here and I'll... Okay, so I just want to show the current draw at 1 volt. So I've got my power supply set here at 1 volt, and I'm going to bypass the diode. So the power supply will be powering the motor. It's set at 1 volt, and you'll be able to see the current draw at 1 volt on this little rotor. So you can see it accelerating. It's actually spinning up at a pretty quick pace considering it's at 1 volt and considering the very low microamp draw. And as the motor accelerates, this draw will just drop down to a balance point. But I just want to point out that for 1 volt, at this low microamp draw, this really is the ideal motor for the crystal cell experiments. The motor I've got on my live feed on laserhacker.com, that motor is not nearly so efficient at creating rotation from a low microamp draw as this one. It's been running for a year and a half. So this little motor is the design, I would say at this point. Still go with the 6 coils, 6 magnets if you just want to run on a crystal cell. If that's your primary objective, is to create a little motor that runs on a crystal cell for years, this is the design. But anyway, we can see that the microamp draw is still continuing to drop. I'm going to give it just a very light blow to kind of speed this process up. Alright, so just that little blow, you can see that it does have a generator effect, contrary to what I posted on the forum. For whatever reason, on the forum I was having a really hard time getting any generation effect with this, and I think it must have been the position of the reed switch. But you can see it's still, the RPM is still above the voltage here at 1 volt, so I'm just going to slow that down, and now what you can see is the rotor stabilizing at its actual microamp draw, and it's going to take a little while. This will climb up some. But what you can do to kind of figure that out is to actually check your RPM as the motor is running. So if I take an RPM reading, what you can see here is that it's running at 39 on the RPM, and it's still not, it's not slowing down. As long as it's not slowing down, then you've actually matched the current draw on the motor. So you can see at 1 volt, we're pulling between 1 to 2, maxing at, I don't know, 3 to 4 microamps, and then on the low end, 2 to 1. It kind of fluctuates up and down there a little bit. So let's go ahead and drop this down even more. Let's drop this down to 0.5 volt. And I'll just get down at the bottom end of where this rotor can still spin. So you can see at 0.5 volt, the rotor still accelerates and spins up. There we go. We're set at 0.5 volt, and you can see what it takes to run one of these motors at 0.5 volt. So really, version 1, perfect for crystal cells. It's what I designed it for. It's really what it's good at. Version 2 is great for high voltage experiments and for trying to see how long you can get it to run on polyester capacitors and stuff along that line. But I am still just so impressed with version 1. If you notice, it's spending almost as much time below the zero as above the zero, and when it's peaking at 1 microamp to a little less than 1 microamp. Okay, I was just checking this one before I wrap up on this little guy with the RPM gauge, and it appears to have stabilized at, let me get this where you can see the screen. It appears to have stabilized at around 17 RPM, 17.1 to 16 revolutions per minute. 17.2, maybe it's accelerating just a little, but it'll fluctuate around there a little bit, but that gives you an idea that at 0.5 volt you get about 17 RPM, and again on the current draw, somewhere between 0 to 1 to 2 microamps. So if I put a smoothing capacitor between this, so it wasn't just directly off the power supply, that would smooth this out, and you would see that this is pulling, because of the bounce of the needle, it's not a constant pull here, but you would see that this is pulling. Well, let's just do it. Okay, so now I've got the power supply at 0.5 volt coming into this polyester film cap bank, and between there and the cap bank I have my microamp meter, and then I'm going between there over to the motor. And that's going to allow this to smooth out and to get an actual smooth reading of the current draw. You can see it's still fluctuating around here a little bit. So I'll cut the video and I'll come back to it when it gets up to speed. Okay, so 0.5 volt, I've let it run for a while. I'd say it's pretty stabilized at between 1 to 2 microamps. Since I have it all hooked up like this with the smoothing cap between the power supply and this, I'm going to go ahead and take one more reading at the lowest voltage setting that it will run at. Okay, so this is the very bottom end on this one. I mean, I might be able to get to run on a little less, but this is on a 1/4 volt, and you can see the RPM is very, very slow. But the fact you'll even run on a 1/4 volt in this, 0 to 1.5, 0 to 2 microamp range is really, really cool. So that's the very bottom end on version 1 that I can find. So 1/4 volt, just idling along. Again, excellent for crystal cell experimenting, research. And so anyway, that's the very bottom end on version 1. So anyway, I will move on to version 2 and do some experiments with that. Okay, so I've got version 2 running on a bank of polyester film capacitors. This gives us a total of 90 microfarads. These are connected in parallel with this one. So 90 microfarads. I'm going to go ahead and blow this one more time, and then I'll stop blowing, and we'll stop the rotor and let it start. Okay, so that makes them nice and charged up from the blowing. Now we'll let it start. And I'll go ahead and do some RPM readings here as the rotor accelerates. Let me get this here where we can read the screen. So you can see that we're at 1,000, about 1,900, 2,000 RPM. And that's from a dead stop. We stopped the rotor. It's spinning up to 2,000, over 2,000 RPM now, just on the polyester film caps. So it looks like it accelerated up to 2,000. I will just say it accelerates up to 2,000 RPMs before the RPM begins to decline a little bit. So that gives us an idea on the actual speed of RPM it'll climb back up to from a dead stop on 90 microfarads polyester film caps. Now I'm just going to go ahead and add some drag because I don't have time this morning to do a lot of let this run down. This is going to take a long time to run down. But this is going to be kind of fun. We're going to add drag to the rotor here. Actually quite a lot of drag. And we'll slow this motor down and then we'll let it start, and we'll slow it down, let it start, just to kind of get an idea. Let me go ahead and get the rest of the energy out of this, and we'll do that. It's going to take a while to get all 90 microfarads out of this cap bank. But we're getting there. So even after all of this energy drain and drag, just leaving it alone at this point is going to bring us up to, I'm going to predict, around 300 RPM or more. So it's pretty good. Huh. Electricity just went out for a second here. So yeah, climbed right up to around 300 RPM and stabilized out, and now is beginning a slow crawl down. So let's go ahead and stop this again. Now that we know that that's where that got to, we'll let it restart and check again here. So I'm running out of time to do it this way, but you can see that we're already back up to 150, 148. It's hard because when you move your hand around at these slower speeds, it changes everything. Let me see if I can get a better reading here. Okay, one. Hold still. Okay, I'm going to say that's at 180 and climbing. Based on this, it's probably back up to over 200 RPM. This is taking too much time, so what I'm going to do at this point is I'm going to disconnect 80 microfarads worth of polyester film cap, and we're going to get this out of the system. And at this point, I'm just going to stop this and see if it can start again on the single 10 microfarad electrolytic cap, and let it run in there because I just don't have time this morning for the rundown. That's one of the reasons I went to these small polyester film caps. This thing is just takes too long on the electrolytic caps to see any differences. So you can see it's gone back up to over 70 RPM just on this 10 microfarad cap, and is still increasing in RPM. So I'm going to leave it at that, folks. It's a really fun little motor to experiment with. Definitely does more with less than anything I've experimented with when it comes to motors. So very interesting, a lot of fun, and can't wait to complete version 3 over here and do some serious experimenting with version 3. I expect to learn a whole lot more with version 3, but that's where version 1 and 2 are at, and hope this video has done a lot to help answer questions and just show people where I'm at in the experimenting with this. So anyway, that's where it's at, folks. Let's all keep experimenting. You never know what we'll discover or find. So, alright, I will talk with you all later.